So I'm going to talk a little bit today about gearing up non-Hermitian quantum field theories for building new models for particle physics. So particle physics beyond the standard model of particle physics. So before I get going, just a few quick thank yous. So firstly, a big thank you to the organizers of this very nice and diverse and interdisciplinary meeting on non-Hermitian physics. Thank you for giving me the opportunity to talk, and thank you all to you also for listening in. And I should also mention my collaborators, so Jean Alexander at King's College London, Carl Bender, John Ellis also at King's College London, and Dries Senyev, a former PhD student of Jean Alexander. So new physics. The standard model of particle physics has had unprecedented success, culminating with the discovery of the Higgs boson in 2012. But there are big questions that remain, and this is a non-exhaustive list of those big questions. The origin of neutrino masses, so why the light neutrino masses of the standard model have a mass and why that mass is so small. While we have some good ideas, some good candidates, we still don't know the origin of those neutrino masses. We also don't have a verified mechanism for the production of the matter-antimatter asymmetry of the universe. Again, we have good theoretical candidates, but none have yet been experimentally or observationally verified directly. There is the hierarchy problem. So the problem of the huge disparity between the electroweak scale and the Planck scale. There's the strong CP problem. And then if we look kind of outwards to the wider universe, we have this problem that 95% of the universe, which is composed of dark matter and dark energy, we don't know the ingredients that make up those missing ingredients. So what are our model building strategies? What are we trying to do to solve these problems and build beyond the standard model of particle physics? Well, one thing we can do is add new degrees of freedom. We can add extra gauge singlets, we could add extra Higgs doublets, we could add heavy neutrinos and generate the light neutrino masses via some seesaw mechanism. We could embed the whole theory in supersymmetry with a view to solving things like the hierarchy problem, and then we'll introduce the various SUSY partners for all of the standard model fields. We could introduce new hidden sectors which might account for dark matter or dark energy. The other thing we can do is start relaxing the assumptions that we put into those models. And we could start changing the number of spatial dimensions, for instance, and we could start adding compactified extra dimensions and introducing towers of Kaluza-Klein states, for instance. Or we could start abandoning assumptions such as Lorentz invariance or locality or CPT invariance. So the question I want to ask is, why not non-hermiticity? Why couldn't hermiticity be one of the underlying assumptions that we abandon when we're model building for particle physics? And so that's one of the main things I want to talk about today. I want to talk a little bit about what the subtleties are in doing that, what this means for how we treat non-Hermitian quantum field theories. And then I want to touch on a few of the potential implications of the toy models that I'm going to play with. So the scalar playground that we're going to look at, so just a simple scalar model in which to construct these ideas, is this one. So I'm going to introduce two complex scalar fields and consider this Lagrangian here, which is the Lagrangian for the C number, so the classical number fields. And you see that it has this non-Hermitian mass term, which is proportional to this parameter mu squared. Why two complex scalar fields? Why is this the simplest model I can write down? Well, if I want to have non-trivial parity and non-trivial time reversal transformations, then this is the minimum number of degrees of freedom I need. Two complex scalar fields gives me 4 degrees of freedom. And if I look at this Lagrangian and think about the PT symmetry naively, then you can see that this is PT symmetric if one of those complex scalar fields is a pseudoscalar. So if it has an odd phase under parity. But actually if we were interested in the non-Hermitian nature of this theory, we can go one step simpler and actually think about the matrix model that's underlying this, which is a matrix model corresponding to the squared mass matrix of this theory, which is the one that's written at the top of this slide here, which is skew symmetric. And the PT symmetry of this Lagrangian translates into the pseudo-hermiticity of this squared mass matrix. So if I act with this parity matrix, which, remembering that the underlying theory was one scalar and one's pseudo-scalar. The parity matrix is diagonal 1 and -1. And so if I act with the parity matrix on this squared mass matrix, then I get the transpose of that squared mass matrix. And the mass spectrum is real so long as we're in the regime of unbroken PT symmetry, which is if this parameter eta that I've defined here is less than 1. And when this parameter eta is equal to 1, then we hit the exceptional point where this mass matrix becomes defective, it has some Jordan canonical form, and we lose an eigenvector. And so these are the eigenvectors for that matrix, again, written in terms of this parameter eta, where now I'm going to take m1 squared greater than m2 squared and mu squared positive, so I can drop all those modulus signs on the expression for eta. As we'd expect, these eigenvectors are not orthogonal with respect to the usual Dirac inner product, which for the matrix model is the expression that I've written here, just the complex inner product. And also, as we might expect, it's not orthonormal with respect to the PT inner product, because one of those eigenvectors, namely the E minus, has a negative norm under the PT inner product. And so many of you may be familiar with the story that was told originally by Bender, Brody, and Jones in this paper in 2002, where we can introduce an additional discrete symmetry, which here I've called C primed, which allows us to construct an inner product that corresponds to a positive definite norm for both of these eigenvectors. I've called it C primed because it is not going to be equal to the charge conjugation operation for the quantum field theories that I'm going to consider. So what is the structure of this C prime matrix? Well, it's related to the matrix that transforms this mass matrix into its diagonal form. Now, because that mass matrix is not Hermitian, that matrix is not orthogonal. So this is not a rotation. Instead, it's a similarity transformation, which is something we might have expected. So the C prime matrix essentially is written in terms of the matrix that transforms us to the mass eigenbases. And the reason for this essentially is because the Flavour eigenstates, they have a perfectly sensible inner product with respect to the Dirac inner product. It's only the Flavour states, the mass eigenstates rather, for which there's a problem. And so this emergence of this C primed is basically telling you that you construct the inner product by rotating, well, transforming into and out of the Flavour bases. So the structure of this C primed matrix actually also follows from the similarity transformations that we might have expected. So the similarity transformations that map this to a Hermitian theory. And I've written the identities here, so we know that the C primed matrix in general can be written as some exponential of some operator minus q times the parity matrix to start with. But actually what I want to do is not use the similarity transformation. So everything that I intend to do, I want to do by working directly with the non-Hermitian Hamiltonian. So what I'm going to refer to as the non-Hermitian frame. Federico, do you have a question, or is that from the previous talk?
No, it's from the previous talk.
No problem.
Sorry.
No worries. So I want to work in the non-Hermitian frame, and the reason for that is because when we go to the infinite degree of freedom limit, so from quantum mechanics to quantum field theory, we have to be we have to worry about what these similarity transformations do, for instance, to the Fock vacuum state. And so I want to avoid those problems by just working directly in the non-Hermitian frame. But that's going to create some other problems for me, which is the thing I want to talk about next. So if we now think about the variational procedure for the Lagrangian I wrote down before, so this one that has these two complex scalar fields, if I naively calculate the Euler-Lagrange equations by varying that Lagrangian with respect to the field and its complex conjugate, so remembering here I'm working with C number field variables, then those two Euler-Lagrange equations are not mutually consistent because of the non-Hermiticity of the Lagrangian. This could suggest that the only solution is the trivial one. The only way to satisfy these two equations is if the solutions are vanishing for the fields, but actually that's not the case. There is actually a prescription that allows us to make sense of this, and that prescription is that we can actually choose one of these pairs of Euler-Lagrange equations to fix the dynamics. And while that sounds pretty crazy, I'm going to justify that from a more first principles discussion later on. But the reason heuristically we can understand why this is okay is because physical observables don't care which choice we make. So the predictions are physically equivalent. And the reason for that is because the difference between these two choices can be absorbed in a field redefinition. Another way of looking at it is the physical observables don't depend on the sign of the non-Hermitian term that I've added to the Lagrangian. So you could think about this in terms of the two different ways that I could analytically continue the corresponding Hermitian theory into the non-Hermitian theory. So what does this mean for the way that continuous symmetry properties are borne out? So if the Euler-Lagrange equations are not mutually consistent, what does this mean for Noether's theorem? Well, what it means is that conserved currents don't correspond to symmetries of the Lagrangian that I wrote down previously. So if we take the variation of the Lagrangian, which is what I've written here, then these two parentheses, which correspond to the left-hand sides of the Euler-Lagrange equations, I can only set one of those to 0. The other will be non-zero if I have a non-trivial solution to the field equations. And so then what this means is that the current, so the divergence of that J nu, that current can only be conserved if the transformation, the symmetry transformation that I'm making of my Lagrangian is such that the variation in the Lagrangian is exactly equal to the term that's left over because the Euler-Lagrange equations are not mutually consistent. So that's rather abstract, but I can give you a concrete example. So for the scalar model, the conserved current is actually this one, which is actually the one that corresponds to a U1 cross U1 global transformation. And what you see is that for the conserved current, we actually have to have opposite charge assignments for the two flavors of the fields, for phi1 and phi2, in order for this current to be conserved. And actually what you see is that in the generator of that transformation, actually the parity matrix is rocking up. And this is related to this picture we have of viable non-Hermitian theories with PT symmetry, of their viability being recast in terms of systems with balanced gain and loss. And so this is one way, I think, to think about this assignment of charges here. But if I make this transformation of the Lagrangian, then you see that it's not invariant, because in the non-Hermitian mass term, this term proportional to mu squared, these complex phases have now appeared. So this U1 cross U1 transformation actually maps me between a one parameter family of non-Hermitian theories, all isospectral. But the variation in the Lagrangian, which is what's written in this final equality here, is precisely the term that is the term left over in the non-vanishing of the other Euler-Lagrange equation. So here I've chosen to define the equations of motion by varying with respect to phi star. So now going further, what if we start spontaneously breaking these kind of global symmetries? So what happens to the Goldstone theorem? Well, if we dig back to the original derivations of the Goldstone theorem, then we know that actually having a conserved current is sufficient to ensure that the Goldstone theorem holds. And so what we can do is take, just to show how this works, if I take the Lagrangian that I played with before, I had some quartic self-coupling, so this phi1 to the 4th power for one of the fields, and I changed the sign of the mass term for the field phi1, so that now I have a wrong sign mass term that gives me non-trivial local minima, and I get this spontaneous symmetry breaking. Of course, there is another subtlety now, which is related to the subtlety of the variational procedure, that I need now to minimize a complex potential. But the same prescription tells me what to do, because in essence, what I'm looking for are static solutions to the equations of motion. So this just tells me that if I've chosen my equations of motion by varying with respect to phi star, then I should minimize the potential u with respect to phi star. And so I can calculate the vacuum expectation values of the fields v1 and v2 here. And the Goldstone theorem goes through. So away from the exceptional point, we have a single massless Goldstone mode, exactly as we would expect in the symmetry broken phase. So what now about the Englert-Braut-Higgs mechanism? So what happens if we gauge the U1 symmetry? So now we want a spontaneously broken local symmetry, spontaneously broken gauge symmetry. Well, the first thing is that gauging the symmetry now is subtle. And the reason for this is because we know that the conserved current corresponds to a transformation that doesn't leave the Lagrangian invariant. So if I were to follow the usual minimal coupling prescription to couple my gauge field to the scalar field, then that would tell me that I should couple to the conserved current. But if I couple to the conserved current, then the non-Hermitian mass term, this term that goes like mu squared, that non-Hermitian mass term is not gauge invariant, and that's a problem. Right? So what we have to do instead is couple to the non-conserved current, so the usual U1 gauge current. But now this leads us to another question, which is how are my Maxwell's equations for this gauge field consistent if I have to couple to a non-conserved current? And then you can always ask me about that. I've got some backup slides on that. So we follow the minimal coupling prescription, but to the conserved current in order to gauge this model. And the bottom line is that the Englert-Braut-Higgs mechanism, just as the Goldstone theorem was, is still borne out. And in fact, by working directly in the non-Hermitian frame, we actually find that the Englert-Braut-Higgs mechanism is borne out all the way to the exceptional point. So in the spontaneously broken phase, we obtain a longitudinal polarization for the gauge field, and that gauge field obtains a mass. Right? And that mass is given by the expression here. This ma squared is the mass of the gauge boson. So it goes like Q, it's gauge coupling to the complex scalar, and then it goes like the sum of the squares of these two vebs. Now at the exceptional point, these vebs become equal. So the exceptional points occur at mu squared equals plus or minus m2 squared. So if I skip back one slide, you'll see that in the expression for the vebs there, this vector of 1 and mu squared over m2 squared becomes a vector of 1s, and the vebs become equal. But the sum of these vebs is still non-vanishing at the exceptional point. So the gauge boson mass is still non-zero at the exceptional point. But this is confusing because we have to normalize all of our states with respect to this C-primed PT inner product to ensure that all of our physical states have positive norms. But this C-prime PT norm should diverge, and in fact it does, at the exceptional point. So the normalization of the Goldstone mode is ill-defined at the exceptional point. So how can it be that that mode gets eaten up to become the longitudinal polarization of the gauge boson? Well, I think the resolution here is that these exceptional points have to be treated distinctly. And in fact, at the exceptional point, that Goldstone mode can be normalized with respect to the standard Hermitian norm, and everything is well defined. And so it still can be eaten up by the gauge boson and to become its longitudinal polarization. So in terms of phenomenology, what's the point in playing all these games? Well, what I've put here are some plots of the masses of the extended Higgs sector for this model. Now, all of these gray regions are physically disallowed regions, and that's what the plot on the right is showing here. So what we're interested in are viable symmetry broken phases. And so this region 1 is actually the symmetric phase. So we don't actually have a symmetry breaking for the choices of parameters in that region 1. This region 2 is actually a PT broken phase in which the squared mass, just m squared, is less than 0, and that's the mass of the charged Higgs and the would-be pseudoscalar. The blue region here is also a PT broken region, and that's the region where the light and heavy Higgs is, their squared masses become complex. So the regions we're actually interested in are these unshaded regions on this plot. So what you can see on the left here are regions where the masses of these various fields become equal. And so this is where you're approaching exceptional points. And I think one of the key things of using non-Hermitian or non-Hermiticity as a potential model building strategy is the fact that this non-Hermitian behavior, the appearance of exceptional points, and the parametric dependence of observables on, for instance, the masses as we approach those exceptional points cannot be reproduced by standard Hermitian model building for particle physics. Right? So it's really providing us with unique phenomenology. And that's why I think this is an interesting direction to take. And to really show that, this is a comparison of the evolution of the same masses, but in a corresponding Hermitian model, so the standard 2 Higgs doublet model. And what you can see, so the horizontal axis on all of these plots is essentially related to the ratio of the two vacuum expectation values of the fields, so the beta parameter. Now, the plots in the left 4 panels and the plots on the two two plots in the right panel, they're essentially analytic continuations of one another. So the non-Hermitian model, this non-Hermitian model of SU2 cross U1 spontaneous symmetry breaking, is like an analytic continuation of the Hermitian case. But what you see is that the phenomenology is very different. So for instance, I want to point out is that the mass of the charged Higgs, so this m squared, that increases as you increase tan squared beta for the Hermitian model, but it actually decreases as you increase this mixing parameter beta for the non-Hermitian model. So this is what's unique about model building in this way, the difference in the parametric dependence of observables. So now taking a step back, everything that I showed you there was discussions at the level of C number variables. So what now if we want to construct from first principles viable non-Hermitian quantum field theories? How do we do the second quantization to write those theories down? Well, actually we can start with the C number fields again, and we can think about what the canonical conjugate variables must be in these field theories. So if I define this doublet, capital phi, which is just the two fields, phi1 and phi2, and I say that that evolves with some Hamiltonian h, well, the Hermitian conjugate of that field and the time derivative of the Hermitian conjugate of that field, well, that must evolve with the Hermitian conjugate of the Hamiltonian. But that's not equal to the Hamiltonian because we're working with a non-Hermitian theory. But if I want to construct canonically conjugate variables, then they both must evolve with the same Hamiltonian. It can't be that one evolves with H and the canonical conjugate variable evolves with H dagger. They have to both evolve with H. So this is clearly insufficient to be able to construct the canonical variables so far. So in fact, the self-consistent non-Hermitian deformation for the theory that I wrote down. So if you imagine taking just a complex scalar field with a Hermitian Hamiltonian that doesn't have this mu squared term, and now I want to deform that to be a non-Hermitian theory by adding this mu squared term, well, I have to both deform the Lagrangian and I have to deform the operators out of which it's built. And so I've introduced this extra field variable phi tilde. And now the Euler-Lagrange equations can be mutually consistent. And so I don't have this problem with the variational procedure anymore if I instead work with this Lagrangian. But actually, the Euler-Lagrange equations are consistent with the Lagrangian that I wrote down before, as long as we maintain this prescription of choosing one set of equations of motion in order to determine the dynamics. So these tilde conjugated fields are actually defined via parity. And so these tilde fields are related to the untilded fields by parity. And the reason for this is the pseudo-hermiticity of the mass matrix. So the fact that parity maps that squared mass matrix into its transpose is the reason why I need these two field variables. But the thing I want to stress is that this choice I had in prescription in the C number model that I talked before originally, which was written in terms of phi star and phi without any tildes, the choice I had in choosing the equations of motion, that choice is still here because I have the choice of which field variable to put the tilde on. I could either put the tilde on the unstarred fields or put them as I have here on the starred field. And this essentially amounts to choosing whether phi evolves with H or phi evolves with H dagger, which is related to the parity conjugate of H, or equivalently related to the choice of the sign of this non-Hermitian term, as I said before. So what does this mean for the second quantization? So that was still all C numbers. Well, now if I want to go to Q numbered field variables, so quantum operators, then then I need to introduce two sets of operators, which I've distinguished by a hat and a check. And these are the operators which may look familiar. They're complicated by the fact that the energy is matrix valued in the Flavour basis. So it has off-diagonal elements, which means we need this full Flavour structure that's hiding inside this field operator. But this hatted operator and the checked operator, they're again related by parity. And you see that the difference between this phi hat and the phi check is that one depends on the energy and one depends on the transpose of that energy matrix. And so we can write down then the second quantized Lagrangian, which is what I've written at the bottom here. But again, I want to stress that there's still this choice. I could write a physically equivalent Lagrangian in terms of phi hat dagger and phi check. The physical observables will still be the same. So heuristically, why this doubling? Well, I've already mentioned that this is what ensures that we have a consistent variational procedure, and we're able to construct canonical conjugate variables. But another way of looking at it is to think in terms of the mass eigenbasis, in terms of the mass. I know eigenfields are not a thing, but the mass eigenfields, or equivalent in terms of the similarity transformation to the Hermitian frame. So I've written down here the fields in the mass eigenbasis, these psi's. And so the fields in the mass eigenbasis are obtained by this similarity transformation, that this matrix R that transformed the mass matrix into its diagonal form. But you see that because that matrix enacts a similarity transformation and not a unitary transformation, then the conjugate variables in the Hermitian frame, this psi hat and psi hat dagger, can't be related to phi hat and phi hat dagger. It's simply inconsistent, and this is why we need these two field variables. So what can we do with this? Well, one nice example we can look at now that we've built up this technology is Flavour oscillations. So we can imagine producing one Flavour eigenstate at some initial time, allowing it to propagate, and then ask what Flavour eigenstate we measure again at some later time. And because the mass matrix, so each Flavour state is some linear combination of mass eigenstates, as these propagate, they'll develop relative phases such that once we make the measurement again, we can find the particle in another Flavour from the one that we produced. So all that technology now, in terms of these checked and hatted operators, we can write down what the consistent conjugate states are in the Flavour basis, and we can write those down in terms of the mass eigenstates. So the Flavour eigenstates are here numbered 1 and 2, and the mass eigenstates here are identified by a plus and a minus. And this section marker here is standing for the C prime PT in a product, or rather the C prime PT conjugate, which here also includes a matrix transposition. And the key thing is the fact that this is a hatted operator and a checked operator acting on the vacuum state to produce these states is why I can have a minus sign in that first expression and a plus sign between the two contributions of the two mass eigenstates in the second line for those Flavour eigenstates. And this is what ensures that we have this the correct orthonormality conditions, both in the Flavour basis at finite times and in the mass eigenbasis at finite times. So now we can go ahead and we can calculate the transition probability. So we can calculate the probability that, given that I produce a Flavour I at the time 0, I observe a Flavour J at the time t. You'll notice that the transition probability that I've defined here is not just the modulus squared with respect to Hermitian conjugation. This is a generalization of that to account for the fact that the inner products have to be constructed with respect to the C prime PT inner product. And that's necessary because this is what's going to ensure unitarity in the sense that all probabilities will add to 1. This is telling us that when we construct the completeness relation for these states, we have to be careful to be using the correct canonical variables to construct that outer product of states in Fock space. But now if we calculate the oscillation and survival probabilities, then what we find is that the probability for Flavour 1 going to Flavour 2 or Flavour 2 going to Flavour 1, vice versa, is actually negative for all etas in the regime of unbroken PT symmetry. And that's clearly a problem, right? We have a probability that's not between 0 and 1. And in fact, even before we get to the exceptional point, so even before we get to eta equals 1, I think it's something like eta bigger than 1 over square root of 2, then we already lose perturbative unitarity in the sense that these probabilities become, the magnitude of these probabilities become larger than 1. And you can see that in the survival probability. The survival probability is larger than 1 for non-zero etas that are even far away from the exceptional point. But unitarity is okay in the sense that the sum of these probabilities is unity, and that's because of this consistent construction of the completeness relation by using the correct canonically conjugate variables. But this is clearly dissatisfying, right? I mean, this is unsatisfactory. I mean, do we have a problem, right? Is there a problem with perturbative unitarity in non-Hermitian quantum field theories? And the answer is no. And the resolution is that we have to be extremely careful about defining asymptotic states in non-Hermitian theories. We have to be careful about defining asymptotic states for particles that undergo mixing anyway, but this seems to be even more problematic in non-Hermitian theories. And so what we can do instead is think about what we can actually observe experimentally, so what the physical observables are, and these correspond to scattering processes. So if you think about a long baseline neutrino experiment, a neutrino oscillation experiment, then the neutrinos are actually appearing as intermediate states in what we actually physically observe, which is some process that produces the neutron beam, the neutrino beam to start with, and some process where we don't observe the neutrinos directly, we observe the recoil of, say, nuclei when they interact again in some far detector. So we really want to be thinking about two by two scattering processes where we have a neutrino in the S channel. So the analog here is I want to have my scalar field that has mixing. I want that to appear in the S channel of some scattering process. I'm not really interested in the external states, so the simplest thing I can do is do source-to-source scattering. So introduce this interaction Hamiltonian, where there are these sources JA and JB, and then just look at the transition A to B. Now what you'll see here is we have to be very careful to make sure that the way in which we source the states is consistent with the PT symmetry, because otherwise we're sort of explicitly breaking it. And that's why there's this relative sign between the second and third terms here, accounting for that PT symmetry. And now if we calculate the squared matrix element, and by squared, I really mean the matrix element and its C prime PT conjugate, then that matrix element looks very much like you would expect to see for the Hermitian theory, the corresponding Hermitian theory. So the numerator goes like mu to the 4. So here is, as I promised, that the physical observable depends only on the 4th power of mu, so therefore is independent of the sign of the mu squared term. You see the denominators are what you would expect for something with mixing. The mu in the numerator here, if mu goes to 0, then this matrix element goes to 0, and that's because we don't have any mixing in the limit mu goes to 0. But this squared matrix element is positive, and the most important thing is that it remains real and perturbative all the way up to and including the exceptional point at which this m plus squared is equal to m minus squared, so where the mass eigenstates, mass eigenvalues emerge. So what about fermions? I've talked very much about scalars, so I just want to give a very quick overview of what we can do in terms of fermions. So there's a very nice non-Hermitian extension of the Dirac theory that we can consider as a toy model. It was introduced by Bender, Jones, and Rivers in 2005, and it's the model written here. So it has this gamma 5, this mass term proportional to gamma 5. I'm working with a gamma 5 that is Hermitian, and so this mu gamma 5 term is anti-Hermitian. So it has an anti-Hermitian mass term. But the mass eigenvalues, which are given below, go like the square of the Hermitian mass parameter minus the square of the anti-Hermitian mass parameter, mu. And so you see that as long as the magnitude of mu is smaller than the magnitude of m, we have real squared masses and a viable theory. Now, the same subtleties of the variational procedure go through, and here I'm still going to work with the C number fields. And we're currently putting together, so Jean Alexander and John Ellis and I, the fermionic counterpart to our paper on how to second quantize scalar theories, and that should be out fairly soon. So the conserved current for this model is this one, where you see this interesting structure that's arisen because of the non-hermiticity, so because of this mu gamma 5 term. And if you write this, this conserved current in terms of the left and right chiral components, you see that they're weighted differently. So the conserved current for the left chiral component and the right chiral component are reweighted. And so what you see that's very interesting is that the exceptional points of this theory, where the eigenmasses go to 0, we actually lose one of the left or right chiral degrees of freedom from the current. But all of these subtleties of Noether's theorem that I explained go through. So this symmetry transformation that leaves this conserved current is precisely the one that gives the correct variation of the Lagrangian. So I realize that I'm running out of time. So just to summarize all of these things. So what this means is that at the exceptional points, we really have a massless theory of right and left chiral Weyl fermions, even though there's a mass in the theory. And actually, if we gauge this model, then we recover the full vector plus axial vector gauge symmetry at the exceptional points, which is extremely interesting. And this also means that massless fermions can undergo Flavour oscillations, and we can embed this entire structure in a non-Hermitian Higgs-Yukawa theory. And this is extremely interesting as a potential explanation for the smallest of light neutrino masses. So just to flash up whether you can embed this in supersymmetry, you can. And the bottom line is that for certain models, actually, even though you write down a supersymmetric theory in terms of chiral superfields, the mass spectrum is not supersymmetric. So non-hermiticity can provide a new route to supersymmetry breaking. So just a few closing remarks. As I've said, Noether's theorem, the Goldstone theorem, and Englert-Braut-Higgs mechanism are all borne out in the non-Hermitian setting. But the key thing is that the parametric dependence is very different to similar Hermitian models. The second quantization, as was the variational procedure in the non-Hermitian frame, is subtle, but we can formulate it consistently. And this allows us, for instance, to treat non-Hermitian Flavour oscillations and ensure that we have perturbative unitarity. There are new possibilities for SUSY breaking. There are potential implications for the neutrino sector, and there are lots of other things to do. So we could look at new sources of CP violation, and we can look at the fermionic second quantization, and these things should be out soon. Thank you all for your time and for listening.
Thank you, Peter. Now, this talk is open for discussion. Is there any questions?
I just have a comment, if I can.
Yeah, please go ahead.
Yes. Hi, Peter.
Hi.
So you mentioned that there is a problem with this oscillation, this probability, which does not is between 0 and 1, right? I know some possible way out. I don't know, maybe I lost the point, but there are people, including myself, which to recover this range of values, just normalize the state, time at each time. This in ordinary quantum mechanics. I don't know if in quantum field theory it works, but I guess it works.
So this was something that we tried, that we considered, and it doesn't work out fully consistent with the rest of the construction. So in the sense that if you build up your second quantization from the ground, and then you don't have this freedom at the end then to adjust the normalization of your states. But I think that the point is, I mean, this is why I stress that there is a resolution, but it comes from thinking about what you can physically observe. The fact that that works out is a result of the fact that the underlying construction is fully self-consistent. The problem is that when you go to write down this transition probability, you've kind of extracted the middle of a physical process by hand. And your process of extracting or sort of amputating the external states, that's what's introduced the problem. And so I believe, I agree with you that you could sort of, you could correct the way you've extracted that intermediate process, for instance, by the way that you've suggested. But if I just want to rely on the ingredients that I built up from the second quantization, then this is the problem that arises. But thank you. Thanks.
Is there any other questions, comments?
Yes, there's another question.
Yeah.
The question is as follows. In your considerations, you often had this parameterization in terms of eta.
Yes, yeah.
Yes, and I'm just wondering why you are not using this very strong structural similarity to chiral transformations, because you can just reshape this eta to chiral plus and chiral minus transformations. You have the similar boost structure just in parameter space. Maybe this could provide some additional intuition. I'm just wondering.
Yeah, I think that's a really interesting idea, actually.
You didn't explore this yet, or?
No, we haven't. I mean, I'd be very happy to talk about that more offline. I mean, there isn't any offline at the moment, but
yes, if you wouldn't mind, we could get in contact, because there are very deep additional structures there sitting. I'm just wondering that you didn't touch them up to now.
No.
Okay.
Thank you. That was really interesting. Thank you.
Okay, thank you.
Okay, so thank you, Peter, for your nice talk.